Okay, let's look at graphs of piecewise functions. I have 3 different examples here. They're all relatively simple. With this first one, f of x equals. Now f of x equals 2x plus 3, which we should recognize as a line equation. mx plus b, it's in slope-intercept form. It equals that particular line when x is less than 1. Alright? But then it equals 4 minus 1/2 x, which is a different line equation. So y equals 4 minus 1/2 x when x is greater than or equal to 1. So when you graph piecewise functions, what you want to do is you want to start with the first one. Graph it as if there are no restrictions. Alright? So I'm just going to graph the line y equals 2x plus 3. Well, here's my 3. It's my y-intercept. My slope is 2. So I would go up 2 and over 1, or down 2 and over 1 to get my line. And then if there were no restrictions, then my line would go on and on forever in both directions. All right? Well, the problem says that this is only true when x is less than 1. So for all of the values, here's x is 1. For all of the x's that are less than 1, then I have this particular line graph. But when x is 1, which is right here, I don't have that line anymore. I have this other line. So I'm going to put a great big hole right here, and I'm going to erase the rest of my line beyond that hole, because this particular line is only good when x is less than 1. Now I'm going to graph the other line as if there are no restrictions. All right? It's just easier that way. So my y-intercept is 4. My slope is negative 1/2. So I'm going to go down 1 and to the right 2, or up 1 and to the left 2. Okay. And then my line would go on and on forever in both directions if there were no restrictions. But there are restrictions on this graph. This is only good, this line is only good when x is greater than or equal to 1. So here's x is equal to 1 right here. So for this much of my graph, from x equals 1 on, I have this line. But when x is less than 1, I don't have this line. This line does not exist when x is less than 1. So I'm going to erase all of the line to the left. So this is what my piecewise graph looks like. There's a gap right here. Okay? Now, let's look at this one. G of x. G of x equals negative x. That's also a line equation. We should recognize that. Remember, this is just y. So y equals negative x. It's still slope-intercept form. There's no y-intercept. You see, it's like plus 0. So my y-intercept is really 0, and my slope is negative 1. So I'm going to graph this line as if there are no restrictions. And so it's a line that would go on and on forever through my origin. All right? Well, there are restrictions to this line. This is only equal to y when x is less than or equal to negative 1. Well, here's x is negative 1 right here. So from this point, from x is equal to negative 1, you see, all the numbers back x is less than negative 1, I have this line right here. But if x is greater than negative 1, I don't. I have a different line. So I'm going to erase the part of my graph that no longer works. All right? Well, now let's look at this equation. So I'm told here that y equals 1 when x is greater than negative 1. You should recognize this as a horizontal line. Remember, horizontal lines are y equals a constant, a number. Well, this is y equals 1. So my horizontal line would be right here through 1 if there were no restrictions. All right, it would be right through there. However, this is only good for when x is greater than negative 1. So I would really have a hole right there, and I would erase this much of my curve because, because when x is a number smaller than -1, I don't have that graph anymore, I have the other one. So this graph, y equals 1, is only good for this portion of my graph. And you notice here, the whole of one graph and the endpoint of the other come together, so you don't have that gap like you have in this graph. All right, now this one looks more complicated. It's actually not going to be. This is a rational function. So y equals this rational graph. Now you remember those are really the complicated graphs, the ugly graphs. But when you're working with rational graphs, you want to factor the numerator and the denominator when possible to understand your graph better. So if I factor the numerator, then I get the following, and you'll notice that I have an x plus 2 in the numerator and the denominator. Well, they're going to go away. So really, my graph is just y equals x minus 2, which again is another line. All right, so I'm going to graph this line as if there are no restrictions. All right, so the y-intercept is -2. The slope is 1. So I'll go up 1 and over 1, or down 1 and over 1. And my line would go on and on and on in both directions if there were no restrictions. Well, it turns out that there's one small restriction. You see, x cannot be -2. That's the only number x can't be. Why can't x be -2? Well, it makes the denominator 0. You see, at -2, I don't have this function anymore. At this value of x, -2, I no longer have a point on this line. So guess what? There's a big fat hole right there. All right, so there's a hole there, but guess what? Y equals 3 when x equals -2. So I do have, now y equals 3 would be a horizontal line normally, but it's only y equals 3 when x equals -2. So at -2, we just have the number 3. We just have a point right there. So I do have a point there, it's just not a point on my other function. All right, so if you look at domain and range for all of these, the domain is all of the numbers x can be. Well, if you look at this graph and you read from left to right, you're going to have a portion of the curve at every x value. Even right here, you'll have a portion of the curve. You have a hole here, but underneath it, right underneath it, you actually have a point, a y value for this x. So there are no x's for which there are no y's. So all the x's are in the domain. That means the domain is -infinity to +infinity. But if you look at the y's, I have my curve showing up at all of these instances. But once I get to this point right here, once I get to y equals 5, I no longer have a curve in this function. So I have no points whose y is 5 or beyond. All of my y's are smaller than 5. So how do we say that? Well, we say they're all -infinity to 5, and 5 is not included. So we have the parentheses. Now, if you look at this graph, again, you can tell all of the x's are included. There's no place where there's not a curve as far as the x's go. So my domain is -infinity to +infinity. There are no x values that I don't have. Okay, I can pick a point anywhere and there's an x value for that point. Now, the range, however, I have none of my curve under here. All of my curve is from this point up. Well, this y value right here, remember range is your y, this y value is 1. So my y values go from 1 all the way up to +infinity. This is going to keep going on and on forever. Now this graph, if you look, I have a point for every single x, even right here. I have a point where x is -2. So I have a point for every single x, therefore my domain is negative infinity to positive infinity. Well, let's look at the y's. The y's, I have y values everywhere except for one place, and that's this hole right here. I have no point anywhere on this graph that has this y value. Well, what is this y value? Well, if you put negative 2 into this line equation right here, y equals negative 2 minus 2, y equals negative 4. That's the y value I'm missing. I'm missing y equals negative 4. So my range is going to be all real numbers, but y cannot equal negative 4. That's one way you can say it. The other way you can write the range is negative infinity to negative 4, union with negative 4 to positive infinity.